Title of your notes is Finding Limits. These are notes, because you didn't have a video this weekend. All right. The limit is the value that a function so the limit is the value that a function, and typically functions are written as like y equals something or f of x equals something. So when I say the function, I really just mean the y coordinate, because you find y by plugging stuff in. So the limit is the value that the y value is approaching as the input, which is the x value, as the input approaches some value. All right, here is our example. We're going to look at f of x equals x minus 1 over 2x squared minus x minus 1. All right, what would happen if I plug 1 in, because I want to see what the y coordinate is when I have an x coordinate of 1. What happens if I plug 1 in? I get 0 on the top. What do I get on the bottom? No. 0 minus 1 is 0, right? So I'd get 0 on the top. If I do 2 times 0 squared minus 0 minus 1, oh, I must have multiplied something wrong. Hold on a second. 2x squared minus 2x plus 1x. Oh, I'm plugging 1 in, not 0. That was silly of me. Okay, so if I plug 1 in the bottom, I get 0. If I plug 1 in the top, I get 0. All right, did we see that? Okay, so I cannot plug 1 in, because if I plug 1 in, I get something in my calculator that doesn't work. Okay, and you can see this if I try to plug 1 in all at the same time. If I do 1 minus 1 divided by 2 times 1 squared minus 1 minus 1, I get an error message because that technically doesn't work. Okay, so if I want to know the limit of 1, and you'll understand that notation more in a little bit, then what I'm going to do first is I'm going to come at 1 from the left side. So a number that's a little bit to the left of 1 would be 0.9. A number that's to the left of 1 but is a little bit closer would be like 0.99. 0.999 would still be to the left, but it would be even closer. And then 0.999. So all I'm doing is I'm picking decimal numbers that are to the left of 1. They're slightly smaller than 1, but they're getting closer and closer to 1. All right, so what I want you to do is in your calculator, I want you to type in x minus 1 in parentheses, divided by, and then in another set of parentheses, 2x squared minus x minus 1. So we're typing that function in, and we're graphing it. And then we're going to plug in these x values. So I'm going to do second trace, option number 1. And first I'm going to plug in 0.9 and I'm going to see what I get. So for this one I get 0.357. And then I'm going to try putting in 0.99. And what do I get? 0.336. All right, and then I'm going to plug in 0.999, 0.334, yep. And then I'm going to plug in 0.9999. Okay, so 0.333. And then if I do 0.99999, okay. And if I did 0.99999999999, oh, now my calculator's getting confused. I did too many. Hold on, let me try 6. 1, 2, 3, 4, 5, 6. All right, so as my x value gets closer and closer to 1, what is my y value getting closer and closer to? 0.333333333, which is what fraction? 1/3. So I would say the limit, as x approaches 1 from the left. So right here, what we're doing is we're writing down a mathematical notation. The limit as x approaches 1 from the left of the function, and you can write f of x if you want to shorthand it, or if you want to write x minus 1 over 2x squared minus x minus 1, you could write that. So the limit as x approaches 1 from the left of the function equals 1/3. So as our decimals get closer and closer to 1 for the x value, our y decimals get closer and closer and closer to 1/3. All right. Okay, now we're going to do it from the right. So a decimal that is slightly to the right of 1 would be like 1.1, 1.01, 1.001, 1.0001, oh, that's the same number. We'll do 4 zeros. So this time I'm looking at decimals on the right side, and they're getting closer and closer to 1 because the decimal is getting smaller and smaller. And I'm going to go ahead and I'm going to do the same thing on the right side. So I'm going to plug in 1.1, and what do I get? Point 313. If I plug in 1.01, 0.331. If I plug in 1.001, 0.333. If I plug in 1.0001, if I plug in 1.00001, so what you'll notice is each time I plug in a decimal that's a little bit closer to 1, the 3's go a little bit further. So our decimal for the y coordinate is getting closer and closer to 1/3 again. So here I'm going to say the limit as x approaches 1 from the right side is also 1/3. And what we'll find is that anytime the left side and the right side are going to the same number, then we can say the limit as x approaches 1 of the function is 1/3. So what I'm saying here, I'm not saying if you plug in 1, you get 1/3. I'm saying it should be that if I plug in 1, I get 1/3. It would make sense if I could plug in 1 and get 1/3. That would be reasonable because the curve is going to be really close to 1/3 on either side. Okay. Now, we've actually been doing problems like this all along. We just did them a slightly different way. So let's look back at that original function. So I have f of x equals x minus 1 over 2x squared minus x minus 1. And what we're going to do with this function is we're going to factor the top and the bottom. Okay? What type of factoring do we have for the bottom? A what? It's a slide divide problem, right? It's got the 2 in the front. So we're going to say 2 times -1 is -2. So we're looking for two numbers that multiply to -2 but add to -1. -2 and +1, so that'd be x minus 2, x plus 1. And then what do we do with the number in the front? We divide it by each of these, right? And then what do I do with these? Okay, so this one would be 2x plus 1. This one would be, so we have an x minus 1 on the top, and on the bottom we have an x minus 1 and a 2x plus 1. And so what do you guys notice about this particular problem if you think about what we've learned so far this unit? The x minus 1's cancel, and what does it mean if the x minus 1's cancel? There's a hole there. So I'm going to say there's a hole in this graph, and it has an x-coordinate of 1. And can I find the y-coordinate of the hole? Yeah, how would I do that? Plug in 1 to the leftovers, right? So I would have 1 over 2 times 1 plus 1. So I would have 1/3. So if I look at the hole, I have the point 1, 1/3. This does not mean I can plug in 1 and get 1/3. I can't. This point is missing off the graph. Does that make sense? So when we drew our pictures, we didn't draw a point right there. We drew a circle that wasn't filled in. We said there should be a point here, but it's missing. Does that make sense? There should be a point there, but it's missing. So in the past, we've learned how to evaluate functions by plugging numbers in and getting points that are really there. With limits, we can plug numbers in that we're not allowed to plug in. So technically, we shouldn't be able to plug in 1, but we know that if we did, we should get 1/3. That's the point that would make sense on the graph, okay? So back up here with your definition of limit, we're going to write a common sense definition of the limit. So this is like mathematical. If I ask you to define the limit, that's what I'm asking you to write. But in your brain, the way you can think of it is the y value that should be there. So when you look at the graph, a y value of 1/3 makes sense, but by plugging in 1, we're not going to get it. It would make sense to get it, but it's never going to happen. Okay? So the definition we're going to think of in our head with the limit is we are finding the y value that should be there. Okay. Now there's, this is one place we're going to do limits. So whenever we're doing a rational function, and you see that there's a hole, you're going to be able to say, okay, the limit as x goes to 1 of that rational function equals 1/3. So we've been doing the math all along. Now you just have a new way of writing the notation to write that answer, okay? There's another type of limit we've been doing all along, and that type of limit is end behavior. So this isn't new. I've been having you do this. And today we're just going to express it as a limit. So it's going to look a little bit different, but it's still going to work the same. So this is the function f of x equals x squared. And if I was to write the end behavior before today, I would have written as x goes to the left forever, the y value does what? It goes up, right? But I wouldn't have said the y value, I would have said f of x, because I wrote the equation as f of x. So as the x value goes left forever, the y value goes up. And I would have said as the x value goes to the right forever, the y value goes up. Okay. So that's how we would have written the end behavior before today. Now that we know that we're learning about limits and we're going to start writing limits, we're going to write it a little differently. So after today, I'm going to write the limit as x goes to the left forever of the function f of x equals positive infinity. So as we go to the left forever, the function goes up. It is a slightly different way of writing it. It means exactly the same thing. Okay? As we look to the left side of the graph, the y value goes up. Exactly the same thing written differently. Okay? So before we were writing it out and kind of, this is the way that people write end behavior when they're kind of transitioning into the idea of limits, but they haven't learned limits yet. And now once we learn how to write limits, then we start to express it that way instead. So the reason I write it as a limit is because I can never actually get to a y coordinate of infinity, right? Just like when I look at the whole, I can't actually get an x coordinate of 1 and a y coordinate of 1/3. I can't actually get that. I can't actually get a y coordinate of infinity. That's why we write it as a limit, because it's not possible. Okay. So here we're going to say the limit as x goes to positive infinity of the function is positive infinity. So we're doing the same thing we did before, we're just writing it a little bit differently. Okay, so I'm going to pass out a packet. Yes, I love me some packets. All right, so when we look at this picture, the thing that we're going to remember, instead of thinking of the actual definition of a limit, we're going to think, what should the y value be? Okay, so this one says find the limit as you look at where x is -6 and you're looking at it on the left side. So if you look on the picture, 1, 2, 3, 4, 5, 6. So -6, these 2 points both have an x value of -6. This one is from the left side, I can see because the curve is on the left. This one is from the right side because the curve is on the right. Okay, so I would say the limit as x goes to -6 from the left is a y value of what? -1. So I'm going to say the y value should be -1. If I look at the x value of -6 from the right side, what should the y value be there? 4. Okay. So sometimes when I look at -6, I see an x or a y value of -1. Sometimes I see a y value of 4. So if I look at -6 in general, can I make a conclusion about what y value should be there? No, because sometimes it's -1, sometimes it's 4. So I'm going to say the limit does not exist, just like Mean Girls. Anybody? The limit does not exist. You know? Ah, yeah. It's the white thing. All right. The next one says the limit as x goes to -3. So we're going to look 1, 2, 3. So I have my left finger coming at -3 from the left side. I have my right finger coming at -3 from the right side. All right. So on the left side, here's the left side. What y coordinate is my finger close to? -3, right? On the right side, what is my finger close to? -3. Anytime my fingers agree with each other, left side and right side, then the limit exists right there. Okay? So here it says the limit from the right side we said was -3. And then here they're not asking about the limit from the left side. They just want to know if the limit exists. And it did, because my fingers were in the same spot. Okay, so the limit for -6 did not exist because my fingers were in 2 different spots for an x value of -6. For an x value of -3, my fingers were in the same spot, which is why that limit did exist. So remember, when I find the limit, I am not saying the y coordinate that is there, because the y coordinate of -3 is not there. That's a hole. I'm saying what y value should be there. The y value that should be there is -3. Okay, did that answer your question? Okay. All right, let's try the next one. So this one says x approaches -1 from the left. So I'm going to use my left finger and come to an x value of -1. I'm going to use my right value and come to -1. So what y value should we have based on the left side, my left finger? 2. What about based on my right finger? 2. So I'm going to say the limit as x approaches -1 from the left is 2. The limit as x approaches -1 from the right is 2. And so what's my conclusion? Overall, the limit is 2. My fingers agreed with each other. Okay? So now I am not saying that that y value really was there. I'm saying that y value should have been there. It makes sense for it to be there. Okay? Now, what y value really was there? Right up here. 3, yeah. So if I actually take the function and I plug 1 into the function, I'm going to get 3 as the answer. But 3 doesn't make sense based on the picture. The answer that would have made sense is 2. 2 is actually where the line came. Okay? So there's a difference between what you get when you actually plug something in and what you should have gotten. The dot here feels weird. It feels kind of random. The limit is what would have made sense to have been there. Okay? All right, so next we have the limit as x goes to 1. So if we're looking at this one, here's an x value of 1. So I'm going to come at it with my left finger. I'm going to come at it with my right finger, and my fingers are in the same spot. So that means my left hand limit and my right hand limit are the same. And what y value should be there? -1. And if you can see that dot right there, it's filled in. That means that that y coordinate that should be there really is there. If I was to plug +1 into the function, I really would get -1 as an answer. So sometimes these end up being the same, sometimes they end up being different. Okay? So the number that was there and the number that should have been there actually were the same number. All right. So next we're going to look at an x value of of 3. So my x value of 3 is right here. There's my x value of 3. So if I get my left finger closer to 3 on the left side and my right finger closer to 3 on the right side, what's happening with my fingers? They're going to go further and further apart, right? What's happening at 3? There's an asymptote right there. So my left finger would go down forever. What y coordinate would that be? negative infinity. So from the left, I would have a negative infinity. From the right, my finger would go up forever. Positive infinity. And so what's my conclusion about 3? Does not exist. Not going to happen. All right. And then last, they're asking us to look at the limit as x goes to 8 from the right. So 8 is over here. So here's 8. They want us to take our right finger and look at what happens. So if I follow this graph to 8 on the right side, what do I see? Negative infinity. My finger's going down forever. And they don't ask about the left side. They just want to know what our conclusion is. So if I follow 8 on the left side and the right side, what's happening? My fingers are together, which means the limit exists. And what would the limit be? Negative infinity, right? Because my fingers are going down forever. No, this, I only plugged, oh, this one should say -1. Hey guys, I wrote this wrong up here. So it should be if I plug in -1, I get 3. So make sure you fix that. I wrote that wrong. Okay, go ahead and turn the page. So now in the packet, there's just a few different pictures. All right, so what I want you guys to do, this one I think is confusing because the lines aren't very long, so I'm going to make this line nice and long. And I'm going to do this one too, make that nice and long. Okay, so there's lots of different pictures. They give us different scenarios. So for the first one, they're asking us about where there's an x value of 3. So I can see that right here, this is where we have our x value of 3. So if I come at an x value of 3 from the left, and I come at the x value of 3 from the right, my fingers are not together. So what's my conclusion already? The limit is not going to exist, okay? So what is the left-hand limit? What's the y value for my left finger? 2. What's the y value for my right finger? -2. So the left-hand limit is 2. The right-hand limit is -2. My fingers did not agree with each other, so the limit does not exist. Okay. Now, if I actually plug in 3, I do get an answer. What answer do I get? What y coordinate is there? 1. That answer really was there. Okay. All right. In number 2, my eyes want to look at this point, but that's not the point they're talking about. In number 2, they're asking us about an x value of -2. And so here's where we're looking. So if I have my left finger follow the graph to -2 and my right finger follow the graph to -2, what do we already know is the case? There really is a limit. My fingers agree with each other. So what y coordinate is my left finger at? 2. What y coordinate is my right finger at? 2. So left finger at 2, right finger at 2. What's the overall limit? 2. And if we look at the graph at an x value of -2, what is the y value actually? It's still 2, yeah. There wasn't a hole there, right? That was an actual point on the graph, so that really was the y value. So here, the limit and the y value happen to be the same thing. Okay. Go ahead and look at the third one. Follow it with your finger, so left side, right side, and see if you can figure out what to write down for number 3. All right, so on number 3, what do we see from the left side? A y value of 3. What do we see from the right side? Y value of 2. What's our conclusion? Does not exist. Now, you can actually plug in 1 And you can get an answer, and what would the answer have been? 2, because there's a filled in dot right there. So the answer would have been a 2. All right, number 4, they're talking about an x value of 0. So down here, this is where the x value is 0. So go ahead and check it from the left side, from the right side. All right, so if we follow it on the left side and we follow it on the right side, what should the limits be? -3 from the left side, -3 from the right side. Our fingers agree. What do you get if you plug 0 in? -3. It's a real point that's there. All right? All right, 5 and 6. All right, go ahead and check your answers for 5 and 6. Yeah, so number 6, the x value of 2 is right here. So if we follow it from the left, my finger's at 1. If I follow it from the right, my finger's at 1. And so the overall limit is 1. But I do notice that if I was to plug in 2, I would not get a y value of 1 because that's a whole. If I was to plug in 2, I would actually get a y value of 3. So the limits are all 1 because that's the y value that should be there. But the y value that's actually there is a 3, even though it doesn't quite make sense. We could figure it out. It has a vertical asymptote of 0. And it has a whole at 2. It would be a piecewise function, actually. It would be a rational function like what we've been doing, but it would also have to have another piece. But, yeah. All right, down here, go ahead and X this out. We are not doing these. Isn't that nice? Yeah, yeah. All right. Now I need you to get your notes out again.
Oh my goodness, I can't wait that long.
All right. So we are going to be finding limits. Are we ready? We're going to be finding limits in the context of rational functions. So there are 3 places we always look for a limit, okay? The first place that we look for a limit is any time a rational function has a whole. And the reason we look for the limit there is because the whole doesn't actually exist, right? It's a spot that's not technically there. And so we look for a limit there. So you guys are used to finding the whole as an x and a y coordinate. We've done that a lot. So if your whole has an x coordinate of A and a y coordinate of B, then for this unit, you are always going to say the limit as x approaches A of the function is B. So the point AB is not actually on the graph, and that's why I write it as a limit. Because it should be there, but it's not. It's missing. Okay? Yep.
So are you that, like, you'd rather just have f of x, or can we just put 1?
F of x is better because well, you would look based on what the equation is written as. So if it's written as f of x equals something, you'd put f of x. If it's written as y equals, you could put y. If it's written as g of x equals, you put g of x. So however they wrote the equation, that's how you write it. All right, the second place that we always look for a a limit is at vertical asymptotes. Got ahead of myself. Now, with the rational functions and finding the holes, we know that the hole is always in the middle of the curve somewhere, and so that's why we can just go ahead and write it exactly like this. For vertical asymptotes, we actually have to check the left-hand side and the right-hand side because we always want to know if the vertical asymptote is something like this, where it goes up and down, so the limit doesn't exist, or if the vertical asymptote is something like this, where they both go the same direction, so they agree with each other. Okay? So when we do vertical asymptotes, we are always going to check the left-hand limit, and we're going to check the right-hand limit, and we're going to check the overall limit. So anytime we look at vertical asymptotes for rational functions, we were going to have to find 3 limits to see what our conclusion is. We do not do that for holes because we know in this context they will always be there. All right, and then the third type of limit we're going to find is our end behavior. So that's the limit as x goes left forever, and the limit as x goes to the right forever. So there are 3 places that we look for our limits. When you guys are doing problems for rational functions and I ask you to find limits, I am not going to tell you the numbers that I want you to find the limit at. I'm going to say find the applicable limits, and these are the applicable limits, okay? So next to this, you might write applicable limits. So you know what I mean by that. Yep. Find all applicable limits. So when I ask for that, I mean holes, vertical asymptotes, and end behavior. Okay?
Some problems can have like all 3.
Some problems can have all 3. Okay? Now, a little note to yourself to remember about end behavior is that the end behavior is always coming from a slant asymptote or oblique. And if the end behavior comes from a slant or oblique, that means that your result is going to be a positive or a negative infinity. Or it can come from a horizontal asymptote. And if it comes from a horizontal asymptote, then it's going to be a number. Okay? So end behavior limits will always come either from a slant asymptote or a horizontal asymptote. And so you can kind of predict based on what it has, what types of answers you're going to get for your end behavior. Okay? All right, so in your packet, you are going to flip to the next page. And it looks like this. And we are going to find all the applicable limits for each of the following, which means we're going to look at holes, we're going to look at vertical asymptotes, we're going to look at the end behavior. Alrighty, so I had it print out and tell you if there was a hole on the graph. So if you look at number 2, actually let's go ahead and start with number 1. We'll look at number 1 first. It says there are no holes, so that means we can ignore the holes. We don't have to find those. But we do have a vertical asymptote. Can anyone tell where it is? It's at 0. So I'm going to write the limit as x goes to 0 from the right, the limit as x goes to 0 from the left, and then the limit as x goes to 0 overall, so I can make my conclusion. And for all of these, I can write f of x, f of x, f of x, or I can write the whole fraction for each of these. F of x is fine? Okay.
No, we can do the fraction.
Perfect. All right. So if we look at 0 from the left, what is the curve doing on the left side of 0? It's going down forever. So that's left side is negative infinity. I did write then left. That's a weird order for me to have done it. Sorry. Making it weird for everybody. Okay. And then if we look at 0 on the right side, what do we see? It's going up forever. Do those two things agree with each other? They do not. So we're going to say does not exist. That's our conclusion. And then we have our left hand, or our end behavior on the left side. And we have our end behavior on the right side. And you can see it by looking at the graph, but you can also see it by looking at the degree of the numerator and the denominator. So this graph has a slant asymptote. And we know that when we have a slant asymptote, our end behavior is either going to be a positive infinity or a negative infinity. So as I look to the left side of my graph, what's it doing? Going up. So that limit is positive infinity. As I look to the right side of my graph, it's going down, and so that's negative infinity. So goodness gracious. So those are all the limits that would be applicable for this problem. All right. Let's try number 2. Do we have it all written down? Yes. Okay, so for number 2, now number 2 starts off by telling us that there's a hole in this graph. So we're going to go ahead and we're going to factor this problem. And why are we going to factor this problem? What's the goal? To plug in 2 so we can find the y coordinate of the hole. Why am I not just trying to plug in 2 right now? It's a hole, it's not really there. I'd get an error message on my calculator. I wouldn't be able to get it. Okay, what happens when you factor the top? Yeah, x plus 2x minus 2, difference of squares. On the bottom, I need to take out that negative first. So I'm finding 2 numbers that multiply to positive 2 that add to negative 3. X minus 1, x minus 2. And you can see from the factors that cancel out that it does confirm that you have a hole at 2. And how do we find the y coordinate of the hole? Plug in the x. So we're going to do 2 plus 2 over negative of 2 minus 1. 4 on top. Negative 1 on bottom. So the hole is the point 2, negative 4. Okay. So for the first limit, we're going to say the limit as x goes to 2. Do you guys want to write f of x or do you want to write the whole fraction? F of x equals negative 4. Okay. Do we have a vertical asymptote? Yep. Where's the vertical asymptote? 1. So the limit as x goes to 1 from the left, the limit as x goes to 1 from the right, the limit as x goes to 1 overall. Now, the notation that I am showing you right now is the shorthand. You can either write it the way I'm writing it right now, or you can write the sentence, the limit as x approaches 1 from the left of the function is.
Alright, write it out.
As in the words. Okay? So this is the shorthand. If you, listen carefully, if you shorthand it any more than this, you do not get credit. Do not shorthand it any more than this. Is it tedious? Yes. Is it annoying? Yes. Do I hate it? Yes. But that's how you have to write it. Okay? This is the shorthand. Your only other option is to write it out in words using a sentence. Okay? All right. So if we look at that vertical asymptote and we look on the left side, what do we see? It goes up, right? It goes up towards the asymptote, so we're going to say positive infinity. on the right side of the asymptote, it goes down. And so what is our overall conclusion? Does not exist. Okay? And then we have to look at the end behavior. So look at the left side and look at the right side. And the end behavior we know is always related to if there's a slant asymptote or a horizontal asymptote. So if we look at this problem, what is there? It's a horizontal asymptote at -1. You can see it. And so that means that the end behavior is -1 and -1. As we follow the graph to the left, it's going to get closer and closer to -1. As we follow the graph to the right, it's going to get closer and closer to -1. That's all it does. Okay. Now on here, this actually is the hole, and I don't know why the computer printed them filled in. So anytime you see that, go ahead and just draw a circle around it so we know that's the hole and that's not actually a point. I do not know why it printed them like that. Okay. Is there another problem on this page that you guys would like to do together?
Number 5.
Number 5? Okay, let's do number 5. So number 5 doesn't have any holes, but what's weird about number 5? Yeah, it has like a bunch of squigglies, but how many vertical asymptotes does it have? 2. It has 2 vertical asymptotes, one at -2 and one at +1. So that means we have a lot of limits to write out because we got to do 3 for each of them. So we're going to say the limit as x approaches -2 from the left, the limit as x approaches -2 from the right, the limit as x approaches -2 overall, the limit as x approaches 1 from the left, the limit as x approaches 1 from the right, the limit as x approaches 1, and then also the end behavior. The limit as x goes to -infinity, the limit as x goes to +infinity. That is a lot of limits we have to find.
No limit. Nothing is impossible.
So these 3 are for the first vertical asymptote, right? -2 from the left, from the right, overall. And then we have the other vertical asymptote from the left, from the right, overall. And then the end behavior, end behavior.
Okay.
This is the shorthand. Yep.
If I get sick, I'm gonna be sick for like 1 minute. I don't take it until noon, so can I come in the morning and take it?
Yeah. So if we look at the first vertical asymptote on the left side, what do we see?
It's going down.
It's going down. It's just a little bit. You can't see very much. But if you look at the first vertical asymptote on the left side, it's going down. So we're going to say -infinity. So if we're looking at that first vertical asymptote on the right side of the first one, it's going up. And so what's our conclusion? Does not exist. All right, and then for the second asymptote on the left side, so there's the asymptote, here's the curve. What's it doing? Going down.
So Ms. Morris, are you going to give us like 3 vertical asymptotes
I mean, if you graph it, you can always see what they are.
But I'm saying like to the point where we have to like do all of this. Like,
Am I going to type it up for you? No, I'm going to say find the applicable limits. All right, and then on the right side, what do you see? Goes up, so that's infinity. And what's your conclusion? Does not exist. Okay. And then for the end behavior, we want to know if we have a slant or a horizontal asymptote. Can you tell from the picture? Is it horizontal or is it slant? It looks like horizontal. It's not slanted, right? That's perfectly horizontal. I can also tell by looking at the equation. The degree on the top is a 1. The degree on the bottom is a 2. So the asymptote is always at 0 if the degree on the top is smaller than the degree on the bottom. So this one has a horizontal asymptote at 0, and so my limit is 0 and 0. As you follow the graph left forever, it's getting close to a y value of 0. As you follow the graph to the right forever, it's getting close to a y value of 0. Okay. Do we need to see another one, or are we ready to do on our own? Okay, so here's the assignment.